Hi, welcome everyone. I'm Fran Curtin and I'm at Memorial University of Newfoundland in Canada, and I'm the chair of IUPAC's ChemRawn committee. And this is the first in our webinar series in collaboration with Beyond Benign. So I'm just going to share my PowerPoint slides. So hopefully you're all excited as I am for Dr. Ashlee Howarth's webinar on adventures in the synthesis of metal organic frameworks. And just thank you all for being here today. Thank you to Ashlee for kicking our series off. And thank you to everybody involved in organizing, particularly Juliana and Chloe behind the scenes. So for those of you that are less familiar with the work of IUPAC, it stands for the International Union of Pure and Applied Chemistry. And there are thousands of volunteers worldwide that work with IUPAC. And our goal is to unite the chemistry community across the world and also help with things like standards, naming of new elements, organizing conferences, and much, much more, but also communicating the importance of chemistry. So ChemRawn is a standing committee of IUPAC. Within IUPAC, there are divisions and standing committees, and our standing committee stands for Chemical Research Applied to World Needs. And so much of what we do is tied in with the Sustainable Development Goals. We have a number of activities ongoing. Either we're leading as a committee or we're collaborating with other committees. One of these is called GCS Day, or Global Conversation on Sustainability, and I'll share more about that on a future slide. Another is on chemistry entrepreneurship in collaboration with the Committee on Chemical Industry, and the current project where we've got this webinar series about chemistry applied to world needs. So a little bit about Beyond Benign, who we're collaborating with on this amazing webinar series. They're a green chemistry education foundation, and their mission is to foster a community that empowers educators to transform chemistry education for a sustainable future through green chemistry. They organize webinars like this, conferences, and I'd like to give a shout out to the GCTLC platform, where you can find out about teaching materials, get some advice for incorporating green chemistry into your courses. Ju is busy putting the links to different websites in the chat, so you can find out more about Beyond Benign and GCTLC there. So GCS Day is led by the International Younger Chemists Network. We've got a hashtag, Sustain for All, and a website there, and it's been running for I think 3 years now. It's every fall, and it's on the day that is the anniversary of when the UN declared the Sustainable Development Goals. And as part of activities for this project, we're actually hosting a symposium at the World Chemistry Congress that's being held in Malaysia. And we're accepting abstracts for that symposium. If you've got anything related to sustainable chemistry, abstract submissions are due by February 28th. So this current project, Promoting Chemistry Applied to World Needs, the goals are to make public high school students and university level chemists are more aware of how chemistry can be applied to world needs. So in the first instance, we're running this series of webinars on different technologies related to sustainable development goals and our IUPAC top 10 emerging technologies. And back in 2019, MOFs were one of the topics for the emerging technologies. And you'll get to learn from Ashlee how amazing they all are. Once we've had a few webinars, we're going to take that information and prepare some little animated videos, 2 to 3 minutes long, that then teachers, both at school, at universities, or if you're trying to communicate with a politician or do outreach in some way, that you can use these to communicate and promote science. So we hope people will find them useful too. So watch out for them. You can find out lots more about the top 10 emerging technologies online. Here's the link for the current year's technologies, but as I said, they've been doing them from 2019, and we actually have a call open now for 2025. So anybody from anywhere in the world at any stage in their life can make a nomination. The form's fairly short and online. And also, we're starting to run a series of papers in Pure and Applied Chemistry, which is IUPAC's journal, on these emerging technologies. So do consider writing a mini review or contributing something there. Before I introduce Ashlee, I just want to promote a couple more webinars, both really in collaboration with Beyond Benign. One is on our entrepreneurship project, where Amy Cannon, a co-founder of Beyond Benign, will be talking about how she started Beyond Benign. And then on February 6th or February 7th, depending where you are in the world, Dr. Junji Nakamura will be speaking about carbon neutrality. So now on to introducing Ashlee. Ashlee is an associate professor and a Concordia University research chair at Concordia University in Montreal. She obtained her undergraduate degree from the University of Western Ontario and then went on to do her PhD in inorganic materials chemistry at the University of British Columbia under the supervision of Mike Wolfe. She then completed an NSERC Postdoctoral Fellowship at Northwestern University with Professor Joseph T. Hupp and Omar Farha, focused on MOF chemistry. At Concordia University, the Howarth Group is focused on the design and synthesis of rare earth cluster-based metal organic frameworks, targeting applications in pollution remediation, catalysis, drug delivery, X-ray detection, and chemical sensing. Ashlee is also the contact point for the green chemistry commitment at Concordia University. So anybody interested in the green chemistry commitment, perhaps you can ask Ashlee a question at the end, as well as answering questions on MOF. So I'm going to stop sharing my screen now and hand the floor to Ashlee.
All right, thank you so much, Fran. I'm just going to share my presentation here. Get a laser pointer going. All right, so thank you so much for the introduction and also for the invitation. I'm really excited to be able to give the first webinar in this series, which seems like it's going to be a very, very exciting series. So today I will tell you a bit about the research in my group, which is all focused on metal organic frameworks, from fundamental things like design and synthesis, all the way to application, with a special focus today on applications in detoxifying chemical warfare agents and treating nuclear wastewater as well. So I'll start by giving an introduction to metal organic frameworks, or MOFs, in case anyone in the audience is new to the topic. So MOFs are most often three-dimensional, porous, and crystalline materials. They're made up of metal nodes bridged by organic linkers. Those metal nodes can be individual metal ions, but they can also be multinuclear clusters or metal chains. The organic linkers can be di, tri, tetratopic, multitopic in nature. And because we have such a large library of nodes and linkers to choose from, the structural possibilities for these scaffolding-like materials are nearly endless. With an understanding of coordination chemistry, we can design and tune the size, shape, and chemical composition of the pores in MOFs for all sorts of applications. And as Dr. Curtin mentioned in her introduction, MOFs were named one of the top 10 emerging technologies in chemistry by IUPAC in 2019. So these are just some examples of the building blocks that we can use to make MOFs. So in addition to the metal nodes being individual metal ions, they can also be multi-nuclear metal clusters that look something like this, or they can be chains that look like this as well. The organic linkers also come in all different shapes and sizes. Most often we use carboxylic acid containing linkers, but we can also use nitrogen containing linkers and others. And I always just like to highlight the IUPAC definition of metal organic frameworks, since MOFs can be two-dimensional or three-dimensional. and they can be crystalline or amorphous. But the most important criteria is that the coordination polymer or network must be open and demonstrate the potential for porosity. So it's really porosity that distinguishes MOFs from other coordination polymers. And so because of their permanent porosity and tunable properties, MOFs have been studied for a wide range of applications. And these are just some examples of some common MOF research areas. So first of all, there's always synthesis, fundamental synthesis, where chemists are constantly looking for new building blocks and ways to make new topologies. This is an example of a uranium-based MOF, which is actually the lowest density MOF ever reported. So not exactly what you would expect for a MOF that's made up of uranium-based nodes, but just kind of highlights how the pore structure and connectivity can be more important for a property like density than the identity of the building units themselves. There's also catalysis, where the MOF metal node, inorganic linker, or guest encapsulated inside the framework could be the catalytic active site. We have sensing, in this case, colorimetric sensing, where we have a MOF that changes color when it detects the acidic byproducts that are given off during a nerve agent detoxification reaction. We also have gas capture, gas storage, and gas separations. This is one of the more commonly studied applications of MOFs, and actually one of the first commercial MOF materials is a material called IonX by Numat Technologies, and it uses a MOF to store and deliver hazardous gases that are used in the semiconductor industry at room temperature and atmospheric pressure. So rather than having to do it under pressure. We also can use MOFs for enzyme encapsulation, so to store enzymes to protect them from degradation from their external environment. This could be for biocatalysis or long-term storage purposes. We also can study MOFs for analyte capture from water, so using MOFs to absorb or catalytically degrade different contaminants in water, and where that water could be industrial wastewater, municipal wastewater, rivers, lakes, streams, oceans. We can also use MOFs as photocatalysts, so where we can strategically make MOFs that have photosensitizers or chromophores as linkers, and where we can use those photosensitizers to generate singlet oxygen and do some selective oxidation chemistry, in this case to detoxify a chemical warfare agent. And I will talk more about that specific application in a few minutes. So my research group at Concordia, it's kind of divided into two main themes, and I'm going to talk about both of those themes today. And so the first one is that we're very interested in the design and synthesis and characterization of rare earth cluster-based MOFs and working towards the applications of these materials. And so these are MOFs that are comprised of rare earth elements, so that includes scandium, yttrium, and the series of lanthanoids on the periodic table, and where the metal node is a multinuclear cluster, rather than an individual ion or a chain. The reason we're interested in this class of materials is because they're relatively underexplored in the literature, so it gives us the opportunity to design and discover new materials that haven't been made before, which is something we find really exciting in my research group. Also, because of the high and variable coordination number of the rare earths, we can gain access to unique MOF building blocks that allow us access to different topologies, some of which are either difficult or impossible to obtain when using other metals on the periodic table. The lanthanoids in particular also have interesting optical and magnetic properties, which we're interested in harnessing for some of the applications that we work on. And finally, we also have rare earth element deposits in northern Quebec and in Canada. And the Canadian government, provincial and federal governments, have been investing a lot of money to work towards mining these elements, separating them from each other, and using them in Quebec and Canadian-made technologies. And so these are just some examples of the rare earth clusters that we have to choose from when we're making these specific class of rare earth cluster-based MOFs. So you can see the diversity in these clusters in terms of the nuclearity, the geometry, and the connectivity. And this type of diversity in building blocks is really exciting as a MOF chemist because we can make so many different structures. But it also poses a very significant synthetic challenge. Because all of these clusters are so easily accessible, it makes controlling the generation of one specific cluster in situ during the solvothermal synthesis of MOFs quite difficult to do. And so if you look into the literature at examples of MOFs that have these cluster building units, especially the high nuclearity ones like the hexa, hepta, and nonanuclear clusters shown here, you'll see that the synthesis most often involves a fluorinated modulator, something like 2-fluorobenzoic acid or 2,6-difluorobenzoic acid. And it was originally thought that these fluorinated modulators were required because the fluoro groups are hydrophobic, they protect the clusters from being degraded or hydrolyzed while they're forming. But more recently, it's been shown that actually some of the bridging ligands in these cluster nodes are bridging fluoroligands as well as the traditional bridging hydroxyligands. So that's giving more insight into why these fluorinated modulators are required to make these MOFs, because they're actually part of the structural building unit, the fluoro groups, I should say. So this slide summarizes our contributions to the field of rare earth cluster-based MOFs over the last 4 years or so, where we've shown that you can make rare earth analogs of a well-known zirconium-based MOF called UIO66. And so the rare earth analogs, much like the zirconium ones, are comprised of 12 connected hexanuclear clusters bridged by these benzene dicarboxylate linkers. And the framework has the overall FCU topology. So the Adowdy research group was the first group to show that you could make these hexanuclear rare earth clusters, and even that you could make MOFs with FCU topology. But my group was the first to actually use the terephthalic acid linker, the original linker of UIO66. Now we can also make, and we have also made, rare earth analogs of a MOF called MOF 808. This is a MOF that has 6 connected rare earth hexanuclear clusters bridged by the trimesic acid linker shown here, and has the overall SPN topology. And we call this MOF rare earth CU45, where CU stands for Concordia University. We've also made a new MOF called rare earth CU10, where here we have a nonanuclear cluster building unit bridged by a tetratopic pyrene linker, and giving a MOF with the overall SHP topology, which I'll talk more about in a minute. So for all 3 of these MOFs, we've been able to make a large series of them using rare earths, including yttrium and lanthanoids ranging from europium to lutetium. And in all cases, although it varies a little bit from batch to batch, and it also varies a little bit from framework to framework, all of the cluster nodes in these MOFs have a mixture of bridging hydroxo and fluoroligands. So the very first project I'm going to talk about, which was one of the first projects in my group, was started by my first PhD student, Victor Quesada Novoa. And one of the things we're really interested in is making new rare earth cluster-based MOFs with this pyrene linker. And I'll explain the significance of the pyrene linker in a few minutes. So I'll admit that when we first started this project, we weren't entirely confident which rare earth cluster building block we would make in situ, or even what the final resulting MOF topology would be. But now that we've been working on these MOFs for over 6 years, we understand a lot more about how to make them and how to control certain building blocks and how to make very specific targeted topologies. But at the time, we weren't so sure. So the first thing that Victor did was synthesize the tetratopic pyrene-based linker. He then reacted it with a rare earth nitrate precursor under conditions that we expected should lead to the generation of a high nuclearity cluster node. So using a fluorinated modulator, also in DMF at 120 degrees Celsius. And from that, he was able to make the new material rare earth CU10, which has these 12 connected non-nuclear cluster building units, which give rise to the double 6-membered ring that's required to generate that SHP topology. And he originally made this MOF with yttrium and terbium. And Victor was able to make these really large and beautiful single crystals of this material, so we could determine the structure using single crystal X-ray diffraction. And you can see their nice hexagonal morphology here under an optical as well as scanning electron microscope. So in addition to those single crystals, Victor can also make this material in bulk as a microcrystalline powder. And so here we can see the powder X-ray diffraction patterns showing that for yttrium and terbium Cu10, the MOFs are crystalline and phase pure. This MOF also has permanent porosity, so we can activate the materials and get these nice type 1 nitrogen gas adsorption isotherms, showing that the MOF has BET areas of around 1,800 meters squared per gram and pores of around 10 angstroms in size. We can see that this MOF is also quite thermally stable. So using thermogravimetric analysis, the MOF decomposes at temperatures greater than 400 degrees Celsius. And we can use diffuse reflectance infrared Fourier transform spectroscopy to see the different IR active functional groups in the MOF. And we do see a small peak around 3,700 wave numbers, which confirms that at least some of the bridging ligands in our cluster are bridging hydroxyl ligands, even though most are probably bridging fluoroligands. So why are we interested in making pyrene-based MOFs? We're interested in this because we want to use these pyrene linkers as photosensitizers to generate singlet oxygen so that we can use that singlet oxygen to selectively oxidize and detoxify mustard gas, a chemical warfare agent. And the reason we're interested in doing this with MOFs is because MOFs give us the opportunity to control the distribution or arrangement of these pyrene photosensitizers in the solid state. So we can use these MOFs as heterogeneous photocatalysts to do this reaction. And we do this using these home-built UV or other colored LED setups, where we use these to irradiate the MOF, especially the photosensitizer, the pyrene, generate the singlet oxygen, and do this selective oxidation chemistry. Now, in our labs at Concordia, we of course don't use the real chemical warfare agent mustard gas, but instead we use a simulant called 2-chloroethyl sulfide, which has similar reactivity but is much safer and easier to handle. And so before I show you the results, I should just briefly explain why are we interested in the detoxification of sulfur mustard in the first place. So we're interested, so first some background, I guess. This is the chemical warfare agent. This is the structure of the compound here. It was first developed in the 1800s and then used in a large-scale attack during World War I. It was during this time it became known as the king of the battle gases because it caused more fatalities than phosgene, chlorine, and cyanogen chloride combined. That's because this compound, it's a very powerful blistering agent. It causes severe burns to the skin, eyes, and respiratory tract. And it does this by readily losing a chloride. It forms a cyclic sulfonium cation, which can alkylate DNA and cause programmed cell death. Now, unfortunately, sulfur mustard is not just a problem from World War I, but there are reports, even fairly recent ones, of this chemical warfare agent being used against soldiers and civilians in various parts of the world. And although most nations have now declared that their bulk stockpiles of sulfur mustard have been disposed of, unfortunately, this compound is quite easy to synthesize. So it would be quite easy to remake and make new bulk stockpiles of this compound, meaning that it's always a potential threat in areas that are under conflict. And so we want to see if we can find a sustainable, environmentally friendly way to detoxify mustard gas. And the reason for that is that the traditional ways that mustard gas has been detoxified, especially bulk stockpiles, is either through dumping this compound in the ocean, where it slowly hydrolyzes and detoxifies over time, but wreaks havoc on the natural ecosystems in the ocean. And also the other way it's been detoxified in the past is through incineration. So through heating to very, very high temperatures, burning the compound, which leads to the generation of sulfur dioxides, hydrochloric acid, and toxic compounds that we don't want being released into our environment. And so we want to see if we can use MOFs as a sustainable alternative for this detoxification. And so this is in line with the UN Sustainable Development Goals, number 9, industry, innovation, and infrastructure, 14, life below water, and 15, life on land. And so when we think about the detoxification of sulfur mustard, there are 3 ways you can do this. There's a hydrolysis pathway. This is what happens when the compound is dumped in the ocean. It slowly hydrolyzes over time. But this pathway releases an acid as well. So not only is it slow, but it releases an acid, so it's not really ideal. There's a dehydrohalogenation pathway, but it requires the use of a base and it liberates an acid. And different side products and byproducts can form that are quite toxic as well. And so we choose to focus on the oxidation pathway, where we can just use molecular oxygen as an oxidant to do this, which is great. But you have to be careful here as well, because the oxidation has to be selective to generate the sulfoxide. Because if you over-oxidize this compound and you generate the sulfone, you end up with a compound that's nearly equally as toxic as mustard gas itself. And so selective oxidation is key for detoxification. And so how can we selectively oxidize sulfides to sulfoxides? So one way you can do this is to use singlet oxygen. And there are also lots of different ways to use singlet oxygen, but one way is to use a photosensitizer. And photosensitizers can be things like pyrene. So how this works very briefly is that the photosensitizer absorbs light and you have the singlet state of your photosensitizer. If you have efficient intersystem crossing, which can be aided by things like heavy metal nodes, like the rare earth clusters in our MOFs, we can generate the triplet state of our photosensitizer. And then if that has the right energy, we can transfer the energy to ground state triplet oxygen to make singlet oxygen, which is the reactive oxygen species that does the work. And so how does Victor do this reaction then? So he takes the mustard gas simulant, the 2-chloroethyl sulfide, he puts it in methanol solvent with the MOF, which is a solid powder and remains a solid powder throughout the whole reaction. He purges the mixture with oxygen to make sure we have an oxygen-saturated environment. And then he irradiates that mixture with a UV LED that excites directly into the pyrene photosensitizers. And here you can see the conversion of the simulant versus time. And so what we see is that this reaction goes to 100% completion. It is selective to generate the sulfoxide. There's no production of the sulfone. And we see that the reaction is quite fast, with half-lives of 5 minutes and 3 minutes, depending on the analog of Cu10 that you use. So these half-lives are actually among the fastest half-lives that have ever been reported for this reaction to date. And we can do it using only 0.5 mole% of the MOF as catalyst. So we can use a very low amount and then only molecular oxygen and some light to do this detoxification. So much better than incinerating the compound or dumping it into the ocean. So we can compare our MOF-based catalysts to some other pyrene-based MOFs that have been reported in the literature before. These are zirconium-based MOFs that also have pyrene-containing linkers. Now, what I think is most important to focus on here is the pore aperture size of the MOF, because that's important for the diffusion of reactants and products throughout the framework. And also what's important is the density of pyrene photosensitizers within the structure, because that's important for the generation of singlet oxygen. So we can see here that with NU1000, we have a MOF with very large pore apertures, but a very low density of pyrene photosensitizers, giving rise to a half-life of 6.2 minutes. NU400 has these quite small pore apertures, you can see here, but a high density of pyrene photosensitizers, but ultimately still giving rise to a slower half-life of 10.2 minutes. And then you can see for our catalysts, yttrium and terbium Cu10, we have a balance between pore aperture size and pyrene density, where we have a moderate pore aperture size, a moderate density of pyrene chromophores, ultimately giving rise to these faster reaction kinetics or shorter half-lives that you see. And so this is something that we thought was really interesting, because this balance between pore aperture size and pyrene density is dictated by MOF topology. And this SHP topology of rare earth Cu10 has so far only been shown to be accessible through the use of rare earth elements, which generate the non-nuclear cluster node that's required to make this MOF and this topology. And so in addition to studying yttrium and terbium Cu10 as photocatalysts for the detoxification of sulfur mustard, we also wanted to learn and understand more about this process and these types of catalysts, because the more we can understand about them, the better equipped we are to design better and better catalysts for this application. And so one thing we also wanted to see is if we made the MOF Cu10 with all of these different lanthanoid analogs, ranging from gadolinium to lutetium, how would the potential for linker to metal energy transfer in these MOFs affect the photocatalytic results that we see? And so it's a well-known phenomenon in the lanthanoid literature that when you have an organic ligand coordinated to a lanthanoid, whether it be a coordination complex or a MOF, if that lanthanoid, if that organic linker has a triplet state, that lies above or higher in energy than the emitting state of the lanthanoid that it's coordinated to, you can observe ligand to metal energy transfer and subsequent metal-based emission from the lanthanoid. And this would potentially be a competitive pathway with the generation of singlet oxygen, since the generation of singlet oxygen also goes through that same pyrene triplet excited state. And so we wanted to see what happens if we make this MOF with gadolinium through lutetium, because in some of these versions, the ones highlighted in pink here, we have the potential for that linker to metal energy transfer or the potential for that competitive pathway. And so the first thing, of course, was Victor had to make all of these MOFs. So these are just the powder X-ray diffraction patterns that show that the materials are crystalline, phase pure, and isostructural. They're also all permanently porous, where we have these nice type 1 nitrogen gas adsorption isotherms and BET areas ranging from 1,500 to 1,900 meters squared per gram. We also need to look at the photophysical properties. So this is the diffuse reflectance UV-vis absorption spectra for all of these MOFs, where you can see that the absorption bands are primarily dominated by pyrene pi-to-pi star transitions, although we do see some FF transitions from some of the lanthanoid ions in the MOF. And we can also look at the solid state emission spectra, where we see that, again, the emission is also dominated by pyrene, where in some cases we see pyrene monomer, and in other cases we see pyrene exomer emission. So we wanted to probe and understand whether or not we actually see energy transfer from the pyrene linker to the metal in the cases where it's theoretically possible. So that's for these 4 lanthanoids here. And in order to probe that, we wanted to look at the near-IR photoluminescence, basically to see if we excite into the pyrene at 405 nanometers, do we observe near-IR photoluminescence from these 4 lanthanides? Because if we do, then that shows that the energy transfer is taking place, and that energy transfer could be a competitive pathway with the generation of singlet oxygen. And so we did this work in collaboration with Dr. Francisco Yabor Villanueva, who at the time was a PhD student in Mark Wilson's group at the University of Toronto. And Francisco collected these near-IR photoluminescence spectra for us, where we see for holmium, erbium, and ytterbium, we see this near-IR metal-based emission, confirming that that linker to metal energy transfer takes place. We didn't see any emission for thulium, but that's expected, as thulium is very well known to undergo cross-relaxation processes, which quenches the metal-based emission. But we could assume that the energy transfer is likely taking place in this MOF as well. And so because those energy transfer processes can compete with the generation of singlet oxygen, how does that affect the photocatalytic results that we see? And so here, we have the photooxidation kinetics for all of these Cu10 analogs, so conversion versus time. What we see for all of these MOFs is that in all cases, the reaction still goes to 100% completion, and it's still selective to generate the sulfoxide, which is great. Also, in all cases, we still see that the catalysts are faster than the zirconium-based MOFs with pyrene linkers, Nu1000 and Nu400. So that's also great. But we do see that some of the MOFs where energy transfer is possible do have longer half-lives or slightly slower photooxidation kinetics than the others, suggesting that there is a bit of competition between that energy transfer pathway and the generation of singlet oxygen, which slows down the half-life just a little bit. Now, these differences of about a minute might not seem very significant, but when we're talking about detoxifying a chemical warfare agent, particularly if we're talking about in personal protective equipment, a minute can make a huge difference. And so one thing, of course, we're continually trying to work on is to get these half-lives for this reaction lower and lower. So some ongoing research in my group related to this is that when Victor was in the process of discovering rare earth Cu10, he also discovered 2 new rare earth MOFs containing the same pyrene linker that we call rare earth Cu06 and rare earth Cu05. These MOFs are quite different than Cu10 in that they contain these rare earth chain nodes rather than rare earth cluster nodes. They also have very different topologies and very different arrangements of the pyrene photosensitizers throughout the structure. Just as kind of a side note, what's interesting about this is that Victor so far has only been able to make rare earth Cu10 with lanthanoids ranging from gadolinium to lutetium. And for rare earth Cu6, this topology and structure only forms when using the early lanthanoids from lanthanum to europium, whereas rare earth Cu5 forms when using the late lanthanoids from gadolinium to lutetium. And so we wanted to look at the photooxidation kinetics, compare it for all three of these different MOFs to try to continue to gain a deeper understanding of what structural features really dictate faster half-lives or better catalysts. And so if we take a look at the best MOF in each series, so that's terbium Cu10, lanthanum Cu06, and scandium Cu05, and we look at the pore apertures and pyrene densities in this MOF, we see that in general, all of these MOFs have what appears to be a nice balance between pore aperture size and pyrene density. And they also have all fairly fast half-lives, although with some differences amongst them. And so what we're starting to believe is that it's not only the balance between pore aperture size and pyrene density that's important, which is what we thought in our original work, but also that the arrangement of the pyrene chromophores or photosensitizers throughout the MOF is also incredibly important, including the distances between them and the geometries at which they pack in relation to each other. And so we hope that as we start putting all of this together, we can continue to design better and better catalysts and get these half-lives for this reaction below 2 minutes, below 1 minute, and actually make this viable not only for bulk stockpile detoxification, but for use in personal protective equipment as well. And so to kind of switch gears a little bit, but staying on the theme of rare earth cluster-based MOFs, another project in my research group is a project that was taken on by Dr. Michaela Ricketsi, who was interested in seeing if she could use an alternative precursor for the synthesis of this rare earth cluster-based MOF here called rare earth UIO66. So in the original synthetic procedure that we developed to make this MOF, we used rare earth nitrate with the terephthalic acid linker, using 2,6-difluorobenzoic acid as a modulator and DMA at 120 degrees Celsius to make the MOF. Now, the issue with using rare earth nitrate precursors, which are the most common precursors used for the synthesis of these types of rare earth cluster-based MOFs throughout the literature, is that rare earth nitrates are very oxidizing and corrosive. Because of that, they're harmful to the environment, and they're also extremely hygroscopic. So they take on a lot of water over time, and because these MOF syntheses are sensitive to water, having a precursor that's continually taking on water, therefore we're adding different amounts of water to our reaction every time, leads to reproducibility issues with the MOF. And so Michaela was interested in seeing if she could replace the rare earth nitrate precursor in this synthesis with rare earth acetate, which is less hygroscopic, less oxidative, corrosive, less harmful to the environment. And this project, or this goal, is in line with one of the UN Sustainability or Sustainable Development Goals number 12, responsible consumption and production. And Michaela specifically wanted to see if she could do this by simply replacing the rare earth nitrate with rare earth acetate, but not changing any of the other synthetic conditions. And she was able to do just that. So here we have the powder X-ray diffraction patterns showing that we can make all of these different analogs of rare earth UIO66, whether we use a rare earth nitrate or rare earth acetate precursor. All the materials are crystalline and phase pure and isostructural to each other. So here on this plot, in each case, the bottom trace is the MOF made with the nitrate, and the top trace is the one made with the acetate. So you can see that they're all the same. We also see that all the porosity and surface areas are the same for MOFs made with the different precursors, but containing the same metal. So here we just have a few examples. You can see the 2 yttrium-based MOFs made with nitrate and acetate, the 2 terbium-based MOFs, and the 2 ytterbium-based MOFs. All have the same nitrogen uptake and BET surface area, whether they're made with the nitrate or acetate. We can also see by scanning electron microscopy that the particle morphology is the same, although we do see some slight differences in sizes depending on the precursor that we use. Michaela also collected diffuse reflectance infrared Fourier transform spectroscopy, where you can see that whether you use the rare earth acetate or nitrate precursor, the spectra nearly perfectly overlap. We can see from the proton NMR spectra that we have all the same components. So we see the proton from the terephthalic acid linker, from water, from the dimethylammonium cation that balances the anionic charge of the MOF, and also from some acetate capping linkers. We also see that whether we use a rare earth nitrate or acetate precursor, the percent yield for the reaction is comparable. And we also see that in both cases, we can improve that percent yield substantially by adding between 100 to 300 microliters of water to the reaction mixture. And so all of this confirms that we can indeed use rare earth acetates in place of rare earth nitrates, which is great because now we can use precursors that are less hygroscopic, less oxidative, corrosive, and harmful to the environment. So before I move on to the secondary theme of my research group, I just wanted to summarize some of the other ongoing work in the area of rare earth cluster-based MOFs that we have been doing or that we're continuing to do in the lab. So we've shown that you can do transmetallation in these materials, which means you can start with a yttrium-based MOF, put it in a solution with a new rare earth precursor, and end up with a daughter MOF that either has a mixed metal node or is completely transmetallated to a new metal. We've also studied the radioluminescence in some of these MOFs, meaning that we can excite these materials using X-rays and observe visible photoluminescence, which is of interest for X-ray detection applications. We're also always looking to make new MOFs, and so this is the new MOF CU45, which is the first rare earth cluster-based MOF with open metal sites that's been reported in the literature. We've also shown that you can make mixed metal analogs of these rare earth cluster-based MOFs, specifically UiO66, and by strategically tuning the composition of terbium, gadolinium, and europium in that cluster node, we can generate a MOF that has white light emission, which is of interest for solid-state lighting applications. We've also shown that you can grow single crystals of all of these MOFs and determine their structure using single crystal X-ray diffraction. And in this particular example, we collected the single crystal X-ray data for all of these analogs and analyzed it and correlated it to certain properties like thermal stability of the materials. And we're also constantly interested in studying the photophysical properties of these MOFs. So this is CU45, made with metals ranging from europium to lutetium. And throughout this series, we can observe tunable photoluminescence from the UV to the visible to the near IR range of the electromagnetic spectrum. So to switch gears a little bit, so the secondary theme in my research group, in addition to the rare earth MOFs, is that we're also very interested in working with zirconium cluster-based MOFs and applying them for new and niche applications. So here what we do is we take zirconium MOFs that have already been reported in the literature by other research groups, so we're not making new materials in this case, but we're applying them for new or niche applications. And so these are some examples of those types of zirconium-based MOFs. They all have hexanuclear cluster nodes. If we have linear ditopic linkers, we can have UiO66 and UiO67. If we have tritopic or tetratopic linkers, we have MOFs like MOF 808 or NU1000. And so one of the things that we're very interested in studying these zirconium-based MOFs for is nuclear wastewater treatment applications. And the motivation for this work, or for some of this work, is that in 2011, a very large magnitude earthquake hit in Fukushima, Japan, and a subsequent tsunami hit the Fukushima nuclear power plant. So this caused a massive meltdown of the plant and quite a large environmental disaster, where there are now over 1 million tons of contaminated coolant water being stored on the site of the Fukushima nuclear power plant. And there are lots of different contaminants that we should be concerned about in this water, but one of them is iodine-129, which is radioactive iodine that has a half-life of 15.7 million years, which means it's going to be around forever, no matter where we end up storing it or putting it. So the iodine-129 in this water is present either as iodide, I-, or iodate, IO3-, the oxyanion. And current methods that are used for the decontamination of this type of water, which is particularly ion exchange resins, they're selective for the removal of iodide, but they have very low capacities for the removal of iodate or other oxyanions. And so we were interested to see if we could find a zirconium-based MOF that could have a high capacity for the absorption of iodate oxyanions, so we could hopefully work towards cleaning up this water. Now, unfortunately, this water is already being dumped into the ocean as we speak, but there's still lots of water that has not been dumped into the ocean that we still have hopes of decontaminating before we end up with the iodine 129 in our waters. And so this research is in line with the UN Sustainable Development Goals 7, affordable and clean energy, 13, climate action, and 14, life below water. And so the MOF that we wanted to study for this application, the removal of iodate from water, is zirconium MOF 808. This was a MOF that was first reported by Omar Yagi's group in 2014, and we thought it should be perfect for this application because it has these quite large 18 angstrom pores, which can accommodate iodate oxyanions. It's made of these 6 connected hexanuclear cluster nodes. So because they are 6 connected, meaning they have 6 connections to make the framework, they also have 6 empty connections or open metal sites that are potential spots that the oxyanions can interact with. This MOF is also made of the commercially available and inexpensive trimesic acid linker, which is great. And Chris Koopman, who is the PhD student in my group that works on this project, makes the MOF using formic acid and DMF at 100 degrees Celsius, and always obtains ththese really nice type 1b nitrogen gas absorption isotherms and surface areas of around 2,000 meters squared per gram. This MOF is also extremely stable. It's stable in water for days and weeks, and it's also stable under acidic and basic conditions, so from about pH 1 to pH 9. So what Chris does is he takes the MOF 808, and he exposes it to aqueous solutions containing iodate oxyanions at varying concentrations. Concentrations ranging from 1 to 3 iodate oxyanions per node. So saying per node is kind of like saying per mole of material. From these absorption kinetics, we can construct a Langmuir plot, which can tell us about the maximum adsorption capacity Q in our material, which tells us that MOF 808 has a maximum capacity of 233 milligrams of iodate per gram of MOF, which is actually one of the highest capacities that's been reported for any adsorbent material in the literature so far. And so we can use scanning electron microscopy coupled with energy dispersive X-ray spectroscopy to kind of start to understand how the iodate is incorporated in the metal organic framework. And so what we can see here is that both the zirconium and the iodine are evenly distributed throughout the crystallites, which is usually a good sign that adsorption is not only taking place on the external surface, but actually in all the internal surfaces of the MOF as well. We can also reuse and recycle this MOF adsorbent. So when we take the MOF loaded with iodate and expose it to hydrochloric acid at increasing concentrations, we can see that we can remove some, in the case of low concentrations of acid, or nearly all of the iodate oxyanions when using higher concentrations of acid. So we can adsorb the iodate, remove it, adsorb it, remove it, and do multiple adsorption-desorption cycles. And throughout all these cycles, we can see that the MOF remains robust. The powder X-ray diffraction patterns show that it's still crystalline and phase pure, regardless of the concentration of acid that we use, and up to at least 3 cycles, which is what we've tried so far. We can also use different techniques to try to understand how those iodate oxyanions are interacting with our MOF. So diffuse reflectance infrared Fourier transform spectroscopy shows us that in the bare MOF without iodate, we have a very sharp band around 3,700 wave numbers corresponding to terminal hydroxyl ligands on the zirconium-based node. And after adsorption of iodate, we see that that peak decreases significantly, giving us insight that those iodate oxyanions may be replacing those terminal and labile hydroxyl ligands on the node of the MOF. We can also use atomic pair distribution function analysis. So this is data that's collected using total X-ray scattering analysis from a synchrotron, where we can get information about specific atom to atom or atom pair distances in our material. And so we can compare the experimental data to a bunch of computational simulations where we simulate all the different ways we can envision iodate interacting with our MOF node. And what we see is that this is the model that fits with the experimental data the best. So showing that our iodate oxyanions are interacting with our node in this bridging fashion. And so all of this shows that we can use this MOF to remove iodate oxyanions from water with high capacity. We can recycle it and reuse the material over and over again. And we also have a very solid understanding of how the iodate is interacting with the framework. And so I wanted to end just quickly by talking about this project in the group where we're always really thinking about more sustainable ways to synthesize our MOFs. So as you probably noticed throughout my whole presentation, all of our MOFs are synthesized in dimethylformamide, or DMF. And DMF is not really an ideal solvent to use. It's hazardous to the environment, it's toxic, it's being banned in the European Union. So we want to try to move away from DMF. And so this project was taken on by a master's student, Paula Marino, in my group, and she wanted to see if we could use this solvent here called Stepisol Met10U in place of DMF to synthesize some typical MOFs. And this is a plant-derived solvent. It's made by Stepan Company in collaboration with Elevance Renewable Sciences, and it's made through a cross-metathesis of plant oils like canola oil with olefins. It also has a really high boiling point, 300 degrees Celsius, so that's great for MOF synthesis, and it's an amide-based solvent, which is important when making MOFs as well. And so this particular project is in line with the UN Sustainable Development Goal number 12, responsible consumption and production. And so Paula showed that she could indeed replace the DMF in the synthesis of all 4 of these MOFs with Stepisol simply by using the same number of milliliters of Stepisol in place of DMF. And so these are just the powder X-ray diffraction patterns showing that all the materials were synthesized and that they're crystalline and phase pure. We can also see that whether the MOF is synthesized in DMF or Stepisol, it has very similar properties, so that it can still be activated, it still has permanent porosity, the BET surface areas and pore volumes are quite comparable, and the percent yields are comparable as well. And this is without even optimizing the synthesis. We can see from scanning electron microscopy that in general, the morphology of the materials remains the same, whether you synthesize them off in DMF or Stepisol. But one difference that we see is the crystallite size. And one thing that was kind of exciting is that in the case of NU1000 and ZIF8, when we used Stepisol, we actually ended up with quite large single crystals that were suitable for single crystal X-ray diffraction. So in addition to replacing DMF with a plant-derived, more sustainable solvent, we may have also stumbled upon a solvent that allows us to make large single crystals of MOFs, which can sometimes be a significant fundamental challenge in the field. We also are able to make MOFs in Stepisol on a large scale. And when I say large scale in our lab, that means a 1 gram scale, since normally we work on the 30 to 50 milligram scale. And so here's just an example showing that we could make H-Coost, a copper-based MOF, in Stepisol on a 1 gram scale. The nice thing about copper MOFs is that they're always this beautiful blue color, and when we activate them, they turn purple due to the removal of a coordinated water ligand on the MOF node. So before I end, I just wanted to give an overview of some of the other research that we're currently doing in my lab in this secondary theme on zirconium cluster-based MOFs and their applications. So we're working on carbon capture using these types of MOFs, and this is in collaboration with government, academic, and industry partners, and this is in line with the UN Sustainable Development Goal 13, climate action. We're also working on using these MOFs for CO2 methanation, so not only capturing the CO2, but converting it to methane, which is a little bit cleaner burning fuel. And this is in collaboration with 3 academic partners and is in line with the UN Sustainable Development Goal number 13 as well. We're also working on using these zirconium-based MOFs to purify recirculating cooling water at nuclear power plants, to work on improving the energy efficiency at nuclear power plants, since currently ion exchange resins require the water to be cooled to lower temperatures before purification. And this is in collaboration with EPRI, the Electric Power Research Institute, as well as Canadian nuclear laboratories, and is in line with the UN Sustainable Development Goal number 7, affordable and clean energy. We're also working on using these MOFs to separate rare earth elements from complex matrices in a more sustainable way. So using MOFs to do adsorption separations, which is more sustainable, hopefully, than the current methods that are being applied in the metallurgical and mining fields. And this is in collaboration with some academic and industry partners and is in line with goal number 12, responsible consumption and production. And so with that, I hope to have shown you some examples of our rare earth and zirconium cluster-based MOFs, that in some cases we can make MOFs that have very fast half-lives for the detoxification of a mustard gas stimulant. In other cases, we can use MOFs that have high uptake of oxyanions relevant to nuclear power applications. Always we're kind of thinking about how we can improve the sustainability of MOF synthesis, and that is a slow but ongoing process that looks promising. And my group is always trying to contribute to both the fundamental understanding of MOF chemistry, as well as the applications of these really exciting materials. And so with that, I'd like to thank my research group. I have a really awesome group of undergraduate, master's, and PhD students, all of the different funding agencies that have supported our work over the last 6 years or so. And also, these are all the collaborators that helped with the research that I presented to you today. And so with that, I'll thank you for your attention, and I'd be happy to answer any questions that you might have.
My God, so awesome. Thank you so much, Ashlee. It was a wonderful presentation. You have a lot of comments in the chat about all of the cool things you're doing. For me, my favorite part is not only like the chemistry, but also the historical and societal aspect that you bring to your presentations, the relationship with the UN and SDGs, and not only like using MOFs to promote sustainability, but also like synthesize them in a way that's sustainable too. So it's awesome. We don't have much time, so I'm gonna go through the questions we had in the chat for you, if you're good. So I'm gonna start with the bottom. We have a question from Andrew. And he's asking that he says that he sees the most of the context for MOFs reactions being with gas. So he's asking about liquids and aqueous as well.
So do you mean, sorry, can you clarify? Is it the synthesis or the application? Maybe I should try to read the question, but I can't find it.
I believe it's applications, but Andrew, yeah.
Okay, yeah, so it's true that the vast majority of MOFs and a lot of the applications that have been reported in the literature are related to gas capture, gas storage, and gas separations. This is kind of historical. It goes back to the fact that the very first MOFs that were ever made in kind of the 60s, 70s, but when they really started taking off in the 90s, were not very stable in water. But they were stable under the presence of gases. So people decided to use and take advantage of the porosity of MOFs for gas capture and gas storage. But in around 2008, when the development of zirconium MOFs started, now we have large libraries of MOFs that are very water stable. And not only are they water stable, but they're stable in the presence of acids and bases. So now, in addition to like traditional gas capture like CO2 or hydrogen, you can also look at acidic gases, but you can also look at using MOFs for removing contaminants from water, because now MOFs are actually stable in water, at least some of them. So I hope that answers your question.
Thank you so much, Ashlee. I'm gonna go just for another one because we don't have much time. But we have a question about has anyone tried modeling the relative importance of pyrene density and pore sizes in terms of reactivity for the detoxification reactions?
No, we have not done any modeling, and nobody in the literature has done that either. That's really interesting, and it would be something that I would love to collaborate with somebody who knows how to do that modeling on. what we have just done is taken everything from the experimental data that we have. So we're trying to compile as much experimental data as possible to try to put the puzzle pieces together and understand what properties are most important. But having for example, like a computational modeler help us not only look at experimental MOFs, but hypothetical MOFs and other MOFs we haven't even made, and see how it can relate to reactivity would be super interesting. So that would be great.
Awesome. Thank you so much, Ashlee. So everyone, we're on top of the hour. So I'm gonna invite you to continue the conversation in our GCTLC platform. So I'm just gonna share my slides here real quick with you so we can close this webinar and move on with our lives. So I think you're seeing my screen, hopefully, in presentation mode. All good. So just a reminder, please, if you have any nominations for the top 10 technologies of IUPAC, please feel free to make a nomination today. Also, if you're working with any of them, please feel free to contribute for the special issue in pure and applied chemistry. Also, as I said, we have a platform that's online and free for everyone. So please continue the conversation in the Green Chemistry teaching and learning community. We created a forum for this webinar series. So if you have any questions, want to ask anything for the MOF community, please go there and keep the discussion going. The other thing I'd like to invite you is for Green Chemistry Connections. These are a webinar series from Beyond Benign that we discuss green chemistry in general. So if you're interested in sustainability, green chemistry, and how we can continue moving towards a more sustainable path, please register for our webinar series to continue with the discussion with us. And this webinar series is more from K through 12, high school fundamental educators. So if you are a teacher and you want to keep the discussion going, please feel free to register for our Observe Wonder Think webinar. And last thing, we hope we can meet you again next month. So February 6th and 7th, please join us again to talk about carbon neutrality and how we can achieve that with Professor Junji Nakamura. So like to thank you all so much for being here today. We're super excited that you joined us. And thank you so much, Ashlee, for your amazing presentation, Fran and Chloe for the support, and we hope we see you again. So thank you.
Thank you.